Okay, it's my pleasure to introduce the Levy lecture of 2019. This is the Levy lecture of 2018. Max is giving also the Levy lecture next year, and that's just amazing. It happened that two scientific committees at the same time, same month, decided that two Levy lectures would be Max. So that shows like the influence and the fact that he's an amazing speaker. I'm putting pressure. Anyway, so Max got his diploma in physics in 1998 in Italy. He got his PhD in theoretical physics from the University of Pisa in 2003. Then he was a maître conférence in Paris Sud in France from 2006 to 2008. Then he was a professor in Paris Dauphine. Then he moved to University of Bonn since 2015, where he holds the Hausdorff Chair. Okay, so join me to give Max the award and the Levy lecture. And his talk is Stochastic Analysis of Quantum Fields.
Great. Thanks, Tuke, even for the organization and the nice conference you put up. Okay. Yeah, so, I mean, this is the last day, and I will try to be kind on you and on me. And I use a very large font so that I could not stick any meaningful formula in my slides. And this, so the talk will be mostly about philosophy of certain approach I would like to explore of approaching a problem of physics, which is quantum field theory, from the point of view of stochastic analysis. And there will be, for me, the aim would be really try to give you a feeling of what is, at least in my point of view, a way to look at quantum field theory and why probability is relevant. So in this topic, which looks like mathematical physics and nothing to do with probability. And after that, why maybe stochastic analysis is relevant, or how you could use stochastic analysis in that endeavor. Recently, there have been many progress in how to understand two-dimensional geometry, random geometry. We see a lot of talks using stochastic analysis. Using SLE was this tool, because then you introduce Brownian motion, you have a time, you have martingales around, and then you have independence. So this is what I mean about stochastic analysis. Okay, how you use a concept like filtration, or concept like stochastic integration, concept like Brownian motion in a topic where a priori it's not so well connected with that, okay? And so let's start. So let's go. Let me start with a personal recollection first, because preparing the talk, I just reminded myself that first time I was in US, it was actually in Chicago, because I was a student in physics, and then I think we are here, and then let's say where it is, I think it's around here. There is so Chicago, it's here. Around here there is the Fermilab, which is a particle accelerator. There are not so many. Okay, there is this one, and essentially there is the one in Geneva. So this is a bit smaller. And I think they don't use it very much. I'm not sure, okay, but okay, the one in Geneva now it's larger, and this I think stopped to getting larger. And then I was a student there for like 3 months in summer. Actually, my first paper is paper coming out from this work, and it's a paper in experimental physics where you have this picture. So I just took it. I don't even remember what was the experimental setup, so don't ask me, because I forgot everything about that. But I still keep the amazement. So there were two amazements. The first one is that it's very fun to work with liquid helium, because it's very fun. It's dangerous, but it's fun. You can drop on the ground, and it just looks like liquid, even if and then it evaporates very fast. But then, and the other amazement was this kind of picture we were measuring. And in this picture, there are these peaks. And these peaks essentially is first, second, three. So they correspond to, so this is the output of a solid state photomultiplier, which is the device we were testing. And these peaks are how many photons you are observing. Okay, this is 1 photon, this peaks is 2 photons, this other peaks is 3 photons. So it was for me very amazing that you see quantum mechanics in macroscopic device, okay? Because that's fundamentally what it is, okay? It tells you that at the very fundamental level, the nature works in a discrete setting, okay? There is no 1.5 photon around, okay? There it's 1 or 2 or 3 and 4, okay? And this is what quantum field theory is, okay? It's try to put together the fact that maybe the space and the symmetry of the space are continuous, but the fundamental nature of nature is discrete. So let's stop about personal recollection. So so this is introduction on quantum field theory, at least how I would like to think about it. And essentially is this, so this is another experimental picture, is a particle coming from here, which generate electron-positron pair and maybe other particle. You see there is also a non-charged particle which goes around here probably and then generate other 2 particles. Okay, so quantum field theory has to account for the creation and destruction of particles. And actually this is a consequence of putting together, you want to put together two physical theories, so quantum mechanics, so this idea that the processes are discrete in a very fundamental level at the Planck, which is regulated, the level it's regulated by the Planck constant. But you want it to put together with this also idea that there is no signal which can go faster than the speed of light, and this is give a special geometry to the space, and this is special relativity. Okay, general relativity is even not well understood how does it work, but even here it's already quite problematic, and the marriage of these 2 theories give rise of quantum field theory. And okay, if you want to know something, I think this is a very good book. Yeah, please. Yeah, okay, this was the old ways. So how you take this kind of picture. So this was taken in a bubble chamber. I think actually I would like to have this kind of thing in my room because it's very nice art. And it's a bubble chamber, so it's a metastable medium. And when the charged particle pass, leave a trace of bubbles, which then you can contrast with some light. Okay, so but it's like in Jeremy Quastel talk where you have the LCD, which is in a metastable state, and then you can initiate a nucleation of the other phase into the first phase. So here there are bubbles, but these are not used anymore. Okay, this is the old way people were studying particle, like I don't know exactly, but maybe before the Second World War even. Okay, then modern ways are what I show you is this solid-state photomultiplier. That is, you have a device which can amplify the passage of particle, and then you can register the mass. The mass you see from the magnetic field. Okay, that's why you put magnetic field, because you want to see the mass by see how fast they rotate in the magnetic field. Okay, anyway, if you want to read something about it, you can open a book like this. This was, I think, written by Steve Weinberg. It's a beautiful book about quantum field theory. And so one way to think, if you are not interested in physics, okay, there is another maybe way to think about it, which maybe can motivate you as motivate me, because you can imagine that actually quantum field theory is nothing else than some kind of non-commutative PDE theory, okay? Because somehow this is geometry of special relativity in the sense that if you are in a given point, you only have access of things which are away from you with the speed of the light, okay? So for example, at this time, I cannot access, so 2 points in space, at the same time, they are not accessible to each other, okay? Because you cannot travel immediately from one to the other, okay? There is no signal that can travel. From this point, you can only access the past in this direction and the future in that direction, okay? And in some sense, you describe this by a wave equation, okay? And you want to describe a field, so fields are like photon fields, okay? It's some property of the space in a given location, or some property of the matter in a given location. And then this field has to satisfy more or less local equations, because there is which encode this fact that signal cannot travel faster than the speed of light. This is encoded by the wave equation. Is the only, essentially, is the most simple differential operator you can write, taking into account the special geometry or special relativity. And then the interaction, if you want to put an interaction, so you want to try to think a nonlinear PDE theory, because you can do linear, okay, but nonlinear is more interesting. If you do linear, you cannot account to creation of particle, okay? There is no interaction between particles, so there is no creation. So you want to put maybe a nonlinear term. This is physical space, and this is time, and they mix together in special relativity, so you cannot separate them very well. Okay, where special relativity, you have rotation, but you have also Lorentz boost, which are like hyperbolic rotation in the space and time. And then, so this is a standard PDE, but then you want to require something very special that is somehow there should be non-commutativity, which at the end of the day, it's this idea that essentially if there is discreteness at the fundamental level, you cannot measure two continuous quantities which are somehow incompatible. And so velocity, so this is like position, and you have to think of this position and velocity at every given point. So this is what is a field, is a mechanical system which has infinite many degrees of freedom, and where the conjugate variables are the position and the velocity. And then essentially you don't have many choice how you set up this commutation rule, because in different point, sorry, this is same time. Actually, it's wrong how it is written. So let me try to get it right. So maybe, yeah, sorry. So this is same time commutation relation, okay? So maybe this is better. Okay, just to say, at the same time, they have to commute in different points because they don't see each other, but of course they anti-commute only at the same point. And this is what creates problem, okay? Because this kind of thing can happen somehow only if these objects are not real function of x and y. You see, this is a Dirac delta, okay? So you have a distribution here, so you can maybe imagine that there is something fishing going on, and you start to set up it properly. And actually, you realize that, okay, you need to set up a non-commutative problem, okay? So the standard way is that you realize your algebra as an algebra of operator in an Hilbert space, okay? That's very concrete realization of some non-commutative algebraic.
Let me ask you a question. What kind of function is FP? What kind of...
Yeah, I mean, you can put, think about linear function is okay, but usually are polynomials, okay? And I will discuss, this is really very sketchy picture, okay?
It's continuous function.
A polynomial, it's okay. It's already quite difficult, okay? Actually, it cannot be any polynomial, okay? But yeah, think about it. There are reasons why, yeah, okay. You just, whatever function you can put, actually, you can put an exponential. That's an interesting theory. I cannot put even very simpler function, okay? I cannot put any function myself, actually, there. But physicists consider, for example, exponential or polynomial. This continuous function, I never saw anything about it. And then the idea is that this field, you have to test it. So it works like this, is that for every test function, phi of the test function is a self-adjoint operator in an Hilbert space. Okay, that's the correct setup that you would like to have. And then you should somehow satisfy, at least in some weak sense, this kind of equation. Okay, so you can think about quantum field theory as PDE non-commutative setting, okay, like non-commutative geometry, okay? So quantum is a way to say non-commutative, okay? So if you don't like, you say non-commutative, it's better. And then people started, in mathematical literature, so started to ask this question, okay, which is the very fundamental question you ask as soon as you start to discuss something. That is for Navier-Stokes theory. Does a solution for Navier-Stokes exist? We don't know, okay, a global solution, okay? And also we don't know if, we don't know if consistent theory of quantum field exists in 4 dimensions, okay? That's 3 plus 1, okay, the relevant one. So this is still an open question. It's one of the Millennium Prize problem, okay, to construct a gauge theory in 4 dimensions and prove their asymptotic freedom and also, okay, other properties, which I don't want to discuss. And then in the 60s, essentially there were an axiomatic approach. So here I'm talking about mathematics now. Okay, you want really to prove that you can somehow give a meaning to this kind of things and construct objects. Okay, so you have an axiomatic approach. You try to write down some axiom and then try to prove that at least you can get out some property from the axiom and that you can construct a model for the axiom. And the axiom looks like this. Okay, you need an Hilbert space. You need somehow the Poincaré group acting as a unitary operator on the Hilbert space. And then you need these fields, which are this distribution-valued self-adjoint operator, that have to have a specific compatibility with the Poincaré group. Okay, so you see how the Poincaré group acts on the Hilbert space is reflected on how it acts on the space variable of the field. And then you need a vacuum vector. Okay, vacuum vector is just this state where nothing moves, there is no particle, so you need a reference state. Okay, but you can't really think in the logic of non-commutative probability. This is the basic data. Okay, you need a measure space and a measure, and here you need a state which is given by this vacuum vector, and you need a measure space, and then you need random variable. Okay, so this is really a minimal setup, but you need to satisfy this, that somehow you have an action on your measure space, if you want, of the Poincaré group. Okay, non-trivial action of the Poincaré group, because it has to do these kind of things. Okay, cannot be trivial. And then so this was worked out by Weitman, and then there were other axioms by Haag and Kassler, which working with this is not very easy because they are self-adjoint operator with all the problem you have, unbounded self-adjoint operator, okay? And you start to ask, for example, I'm very slow, but that's fine. You start to ask, for example, and then people, 4 dimension, nobody starts, so they start in 1 plus 1. So this is, I will call 2 dimension, okay? But keep in mind that it's not 2 physical dimension, there is always time. So 1 plus 1, and then, we can do it. And Nelson, Glim, Jaffe also provided solution, so constructed example of this setup. And then at some point, but it was difficult already in 1 plus 1 dimension, okay? And then there were this idea of Euclidean quantum field theory, which is essentially this idea that you go from time to imaginary time, and then the wave operator becomes the Laplacian, okay, because you change sign or the wrong thing. And physically, it's just, you can't give a meaning mathematically to this as an analytic continuation of functions which depend on t. You continue you prove that you can continue on the imaginary axis. And what they noted is that when you do this, so when you look at the fields on imaginary time, then they look like actually a probability problem. Okay, the point is that Nelson proved that he could somehow reconstruct if he has measured with some property, notion of spatial Markov property, or and other feature I will tell you later, you can reconstruct the Hilbert space. And so let me introduce, so these are the basic objects you will try to, in this approach you try to use. That is, you have a measure, now it's a probability measure on on S prime, so on distribution, and you have a certain correlation function for this measure, and you construct these functions. Okay, so this is a probabilistic object, but they understood by that time, so this was the 60s, 70s, that if this probabilistic object has certain feature, then you can construct an Hilbert space satisfying the previous axioms. Okay, so that's the connection with probability. It's an abstract connection. It's not very concrete. There is no physical meaning in this probability measure, but probability is better than working with operators, okay, because you work with commutative random variable. Okay, so now changing time in this way removed the non-commutativity, but it keep it in other feature of the model. And the idea is that now you have another set of axioms, which I will not discuss very much, but the idea is that you can have axiom for this, so for this set of functions, you can construct axioms, and if you satisfy these axioms, there is an abstract machinery which gives you back the data I showed you before. So I'm going back, and then essentially you can construct these objects. Okay, you can construct the Hilbert space, you can construct energy representation and the fields. Okay, so this is the connection. It's not very intuitive, but it's not very difficult either, okay? It's more or less some kind of GNS construction, okay? Once you have a probability measure, so the important property, these are technical facts, okay? You need that your correlation function has some growth bound, you need some symmetry of the correlation function, but that's automatic in the setting I gave you before, because just they say that you can shift the fields. But these two are the important ones, okay? Euclidean invariants give you back Poincare invariants, okay? This is the magic that is, you can study property of the Poincare group with property of the Euclidean group, okay? So in the probabilistic setup, there is no special relativity, there is standard Euclidean geometry. And then reflection positivity, this is a tricky property introduced by Osterwalder and Schrader. In some sense, what happens is that in the Euclidean space, you need a notion of, there is no notion of time, of course, okay, because you have all the rotations, so there are only space. So reflection positivity is what make a difference between one of direction of the space and the other in the Euclidean domain, okay? And what you are doing, so I don't look at there, what you are doing is that you take a plane, and then you take, so theta is the reflection of functions from one side of the plane to the other side of the plane, okay? So you change the sign of one of the Euclidean coordinates, let's say the first one, okay? So this reflection, you can act on functions on that, and then you require that when a function is paired with its mirror image, somehow it has average which is positive, okay? So look back for correlation function, okay? Essentially, you look at the fields here, and you look at the field on its mirror image, and then you try to look correlation function for that, and this has to be positive, okay? This is some kind of, it's called reflection positivity for this reason, okay? It's some kind of positivity which is not clear a priori, okay? But these allow to construct then the scalar product for the Hilbert space, okay? The Hilbert space will be essentially given by function concentrated on one part of space, and then the conjugation will be this symmetrization, this reflection, and then this will become the scalar product. So it has to be positive. Okay, that they are the important properties. Okay, and they are very tricky. So as soon as you start to work, you see that constructing model which have all this property, even if you have a probabilistic setup, is not obvious. Actually, it's quite difficult, and there is another book, so I will show you many books, okay? This is another important book where all the progress in the understanding of this Euclidean and even in the axiomatic approach were written, and this a story which goes on from essentially, from the 70s and many contributors, and which produced also a lot of other mathematics, okay? We saw, for example, FKG inequalities, and they are very important in this setting.
And is it related with Schwarz reflection principle?
Sorry?
Schwarz reflection in Euclidean spaces. That reflection is related?
Yeah, this I don't know. I don't think so. I don't think so. It's more, it's not, you see, you are taking, it's a property of a probability measure. It's not a property of the space, okay? The probability measure you're using has to be reflection positive. And then in discrete models, you can show it. And actually, it's very powerful to prove theorems about statistical mechanics. And it's also, I discovered recently that it's using representation theory of groups because give you this connection between one group, like Poincaré group, and Euclidean group. Okay, so representation are connected via reflection positivity. And you have a notion of Cartan dual of a group, okay, which is related to this imaginary rotation. What I wanted to say, yeah, I mean, it's reflection positivity, for example, is easy to show for discrete model, but in discrete model, you don't have Euclidean invariance. And in models where you have Euclidean invariance, it's difficult usually to show reflection positivity. So, okay, here I put a lot of reference, but just to give names, and the point is that, so they did 1 + 1 dimension, and with all this technology, they could do 2 + 1 dimension, okay? And I stop at 2 + 1 because nobody can do 3 + 1, okay? That's open problem. It's already 2 + 1 is not written in this book because, so the book is all about 1 + 1 dimension, and then there is a final chapter where it explained that there are many papers on 2 + 1, but you start to read the paper and they're not very easy, okay? And there are a lot of people, so essentially I will explain you what is 543, but essentially it's one of the simplest model you can, actually, it's the only one I know it has been constructed in 3 dimension. Yeah, there are other models, but let's say this is like a very useful model, very simple to state and still already quite challenging, where you can try technology. Okay, because you are still very far from the goal, okay? The goal is to look at 4 dimensions, but you have to develop technology. So the idea is that how you approach the problem of construction. So remember, the goal for me now, it's really, so the goal is really find a measure which satisfies these axioms, and somehow which has other desirable property, okay? But already finding measures which satisfy these, it's easy to find Gaussian measure which satisfy this. As far as non-Gaussian measure, it's more complicated, okay? Yeah, I mean, this story is very complicated, okay? I'm not telling you all the truth, so just keep the vague message, okay? I could just speak about it all the day. And so now I want to speak about stochastic analysis, okay? And from my point of view, for the point of view I'm interested here now, what happened is that Ito and Döblin, but we knew too late about it, somehow wanted to have a description of diffusion process via sample paths. Okay, because if you look at them at Markov process, then essentially this is what you see. Okay, you see a family of marginals, and then you see these marginals are connected via transition probabilities. Then, of course, you can construct a process out of it, but this is all what you see, okay? Measure and connection, non-trivial connection, because even constructing the semi-group is a non-trivial task, okay? You don't have explicit formula, you don't have explicit description, you have only maybe PDEs, and you have to solve PDEs, okay? This was original approach. And then they converted this problem into that problem, okay? Now, in Ito point of view, if you want to construct, this is very simple, but okay, if you want to construct a diffusion process, you have to solve an ODE, essentially. Okay, this is an ODE. And then you start to work about it, and you can do many more things that you can do here. Actually, that's the usual approach we use now. Okay, we construct, first of all, the paths, and then we go back and we construct the Markov process. We prove that this is Markov and that it has all the nice properties. And what are the advantages? It's lower dimensional problem. Okay, here you work with measure, and here you work with sample, with the functions on some space. You can use a fixed point theorem, okay, to solve this problem. Okay, here I don't know of any fixed point theorem you can use to construct. Of course, you can solve the Kolmogorov equation, but it's a PD, it's already higher dimensional than an ODE. And then you have intuition about what's going on, okay, because you will see what's going. So you can stop the process when it reaches a region which you don't like. You can analyze better in other situations. Here it's more complicated. And then, but this is what the important point I want to stress, that there exists a canonical reference object, okay? And this was the idea of Ito, okay? They wanted to reduce any diffusion to very basic fundamental characteristics, which are Brownian motion or Poisson process. But the point is that you have, even the diffusion is complicated. In this equation, there is always an object which you know very well, which is not scaring, is the Brownian motion. Okay, and then you can set up stochastic calculus, and then you discover Ito processes, and then you discover that you can do for semi-martingale, blah, 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 blah. You can do for rough path if you want to use a rough path, but the idea is the same, is that there is an object which you know very well, and then you can construct out of it more complicated objects, okay? SLE has the same philosophy somehow in the two-dimensional context of random geometry, that is, you have a Brownian motion, and out of it you can construct this growth phenomena, okay? And, okay, and then out of this, you produce this amazing. When I came from physics, I was very surprised that you can write like 200 pages book on Brownian motion. Okay, for me, Brownian motion was very simple, and then other things were more complicated. But these two books essentially are what kind of result you can have if you start to look into this perspective to Brownian diffusion in this perspective. Okay, and the point is that when you want then to look at diffusion in infinite dimensions, then this is really fundamental, okay? Because the Kolmogorov equation become even more infinite dimensional, okay? And in this book, you always use the Ito approach to study the measures, okay? So that's the point, okay? And so let's go on. So what is stochastic quantization? So you see, I don't have formulas, okay? So you cannot complain about wrong signs. So what is stochastic quantization? Stochastic quantization is, broadly speaking, relation between a probability measure and an equation, and a stochastic differential equation, okay? Is not this, so I go back, is not this relation, okay? This, of course, is a relation between an equation and a measure. Is somehow a more subtle relation, but you know it very well. But okay, let's keep it. I want to really emphasize this idea, okay, that you want to study a measure. Remember, our goal is to construct some measure which satisfy our axioms, and these measures are very complicated, and so you want to analyze them in some way, and the way you would like to analyze them is to construct an equation which somehow contain information about this measure. For the same reason, Ito wanted to have an equation to construct diffusion processes, okay? And this was somehow introduced by Parisi. So Parisi will appear it appeared in the KPZ equation talk, because one of the people is Parisi. Then it appeared in the Parisi solution of spin glasses, and now it reappears because more or less around the same time, he advocated this idea to construct gauge theory. Okay, it was not rigorous paper, of course, it's physics, but the point is that even in the physics community, it was a new idea, and it was called stochastic quantization. Okay, because you use stochastic equation to construct the probability measure, which will give you a quantum theory. Okay, that's why quantization entered into this name. And if you think about it, it's very natural. Okay, what are Monte Carlo Markov chain method? You are interested in some probability measure, and then sampling from this measure, it's very complicated, but you can construct a Markov chain which converges to equilibrium to that measure, and then on the computer it's very easy to simulate. Okay, you simulate the Markov chain, you wait a bit, and then you have maybe some guarantee that what you see is extracted from the limiting measure. Okay, that's the theoretical version of this. Okay, you're using an equation to study a measure. Okay, and there is few flavors of stochastic quantization. So the first one is parabolic, the usual one, maybe the only one you know. I will show you two others which are more unusual. That is, you look at longevity. So you want to study this measure. So even think in one dimension, that's fine. Okay, it's a Gibbs measure with some weighting function. And then you want to study this measure, and then you know that you can do a diffusion with a Brownian motion which converge to this measure. Or if you start from the measure, stay on the measure. Okay? So the measure, it's invariant, and usually, maybe in nice situation, it's the only ergodic invariant measure for this process. And idea, okay, why this is called stochastic? What is the idea inside this is that, again, you are interested in this object. So, of course, this is something you know very well, okay? It's theory of Markov process, invariant measure, ergodicity. These are the keywords you want to use, okay? But the philosophy is different, okay? You're not starting from here. What you want to study, it's really this kind of object, okay? Because the measures, the candidate for reflection positivity and clear invariance essentially have this form. And you introduce a fictive time evolution, which has this measure as invariant, essentially like Monte Carlo Markov chain method do. And the point is that why the question is simple, okay, seems more complicated, but actually it's simpler, and it requires some time to think about it, because there is somehow I never thought before really thinking seriously what's going on in some theorems. And then the point is that here you have the Brownian motion. Here there is no basic reference object, okay? This measure, usually even this measure does not have a density, so this is really a formal way to look at them. You construct as in limiting procedure, so you start from like a perturbation of some reference measure, but in the limit they are not absolutely continuous anymore, so you don't have any object you recognize very well, but here there is always this object which you know very well, okay? You perturb. Essentially, it's a nonlinear evolution where you feed in a very Gaussian noise. Okay, and why Gaussian? Why not? Is because it works. So you use the simplest tool that makes things work. And then when you start to look at very simple models, so I'm giving you very formally what is the kind of model you want to look. Okay, the potentials you want to look at is like this kind of H1 norm, and then polynomials. Okay. And then when you try to construct this measure, okay, if there were no quartic part, this is the Gaussian free field or the massive Gaussian free field, and then you have to add interaction on top of that. And the question, you see, the question out for this kind of potential looks like some kind of parabolic, nonlinear, semi-linear SPDs, okay, because this noise is white in time, but then if you have space dimension, it's also white in space. So now, don't be confused, okay? This what I call time here, it's a fictitious time, okay? There is no physical meaning in this time. It's the time you use in your simulation. It's the time you use to run your evolution. But the important point is that these fields live in R3, which is the Euclidean space for the R2 plus 1 dimensional Minkowski space, okay? So we are not yet in the physical dimension, okay? Here we are still in a game toy world where the space dimension are two-dimensional, there is one time, so overall you have 3 dimensions. When you do in the Euclidean space, you have 3 dimensions, and you add an additional time, which is just a technical tool. And then you start to look at this equation seriously. For example, when here you have 1 or 2 or 3, and in one dimension, it's relatively easy. In 2 dimensions, it's more complicated because solutions are distributions. That's why you have to put an infinity here. This equation cannot be interpreted literally, even using stochastic calculus. And there were work in the 85 by Ion Arazini and Mitter to give a meaning to this equation. There were other works. I think an important work was this work of Daprat and de Bush, where they found the right and easy method to deal with this equation. And then more recent work was Murray and Weber, which proved that they can do in R2 in the full space. And then more property of this equation were proved in these papers. And then when you try, then, okay, you say, I understood, I go in the higher dimension, so R equal 3, so still is not the physical dimension, okay? We don't know how to do physical dimension. Actually, maybe people think does not exist. Actually, maybe it does not exist in 4 dimension, but let's say 3 dimension, and that has been essentially the breakthrough of Martin Heirer, which invented regularity structure exactly to one of the motivation was to solve the equation. Okay, one inspiration is that, okay, I need to solve this equation. What are the tools I need to construct to solve it? And you need regularity structures. So you need a way to describe locally. The solution is a distribution, so the cube is not well defined, and the derivative is not well defined, but somehow all these things together make sense. Okay, and then you need to see how they interact, so you need to use a very fine description of how they look like. And with Imkeller and Perkowski, we introduced these other different tools, which essentially can be used to solve the same problem. And then there were another approach by Kupiainen, and other people worked on the problem. Now we know very well many properties of solution to this equation, and we can construct solution in the full space. And what is the idea? Okay, and then using this idea and these tools, you can construct a new measure out of them. Okay, you can construct one measure that satisfies the axioms. Okay, so we have together with Martin Hoffmanova, we wrote a paper. Somehow it was clear from our understanding that it was possible, but to convince other people, you should really do it, and do it in the proper way, proving many things. So it took us some time, but it's not very complicated, and should be readable from people that are physicists or theoretical physicists, maybe. And in this paper, we prove that somehow we can construct a measure which satisfies most of the axioms. Okay, we cannot satisfy all the axioms. That's an open problem. And the idea is in this picture. Okay, your SPDE give a relation between the measure and the solution of the equation. Essentially, what you do is that you construct a stationary solution of the SPDE, let's say, and then at a given time, this is the measure you want. Okay, and from the stationary solution, just looking pathwise without any probability, just using analysis, you find bounds on the solution only in terms of the noise. Okay, so this is a very complicated nonlinear object, but here you have a linear object. Okay, so this is the Gaussian white noise. And then from the information on the law of the noise, you derive information on the law of the process, and this gives you a construction of the measure. Okay, this measure has to live in the full space. It's not very easy. Okay, imagine this equation has to be solved in the full space. Okay, so the noise is everywhere. The solution is different from zero everywhere. You cannot use standard spaces. Okay, you have to solve in spaces with weights, and you have to do things, but at the end of the day, it works. It's not very complicated either. So the main novelty is that this proof is quite, okay, for people who know stochastic analysis, is more reachable than the original proofs of the existence of this measure. Okay. Yeah. And now I want to describe other ways to do stochastic quantization, okay, just to tell you there are other ways, okay. They are not as effective because we know less about them, but for example, let me skip, okay. This is a canonical way, this is a way to use wave equations instead of parabolic equation to do stochastic quantization. I will go back later. I want to give you I want to talk a bit about this other way because maybe it's interesting also to probabilists. For me, it's a mystery. I know I can prove a theorem, but still remain a mystery. And this was discovered by Parisi again. Okay, this is another. It's the same Parisi, by the way. Okay, it's another work of Parisi, and they proved and they discovered. So physicists. So this is a discovery. Okay, because you don't know, and I'm telling you now, and I think you didn't know before, so you will learn at least one new thing today, and this is a probabilistic fact, okay? You look, so this is very simple, okay? Imagine lambda is not here, it's just a point, okay? So this is a two-dimensional, a function on two dimensions, real function on two-dimensional space, okay? And which solve this elliptic equation now, okay? Z is two-dimensional, this is Laplacian, you have a potential, and you have a space. There is no time in this problem, okay? Only space. Space is two-dimensional. You have white noise, okay? You can do on the lattice, but what I will say will not work. You have to do in the continuum space. So you can solve this elliptic equation. Okay, for example, if the potential is convex, I can prove that this elliptic equation has one stationary solution in the full space. Okay, that's the problem with the elliptic equation is that you don't have boundary condition in the full space. Okay, but you can prove under some condition, put the condition you want, and there is a unique solution. The claim is that now is a stationary solution, but there is no stationary in space. If it's unique, then you look at a given point, could be 0, it could be another point, anyway it's stationary, the law of the process at that point, and the law of the process at that point is given by this measure. Okay, and so now if lambda is a point, this is really a probability measure on R. Okay, so this is the Lebesgue measure on R, and this is the potential you put there. This is the derivative of that potential, and then there is a 4 pi. Okay, but that's a theorem now. Okay, we proved it, and at least in 0 dimension, when the potential is convex, that's a theorem. Now you start to think about it. There is no way I know easy way to prove this. Okay. This is equivalent of the Langevin equation. Okay, the Langevin equation is a stationary measure. When you look at some point, you know what is the measure. You know what is the law. Okay, so it's some non-Markovian analog of the same phenomenon. Okay, there is no time here. You cannot use any Markov property. There is no easy Markov property out of this elliptic equation. You have, yeah, maybe there is. Okay, but not easy like one-dimensional Markov property. And then the physicists discovered by doing perturbative computation that actually this fact, okay, that the law is computable. And Parisi-Surlas gave a non-perturbative proof in the physical jargon. But the proof uses supersymmetry. Now, supersymmetry is a scaring word, but the idea is that it's like, okay, it's not very different from when you solve the Ising model, you have to introduce fermions to solve the Ising model. Onsager proof of the solution of Ising model can be restated in the fact that Ising model is just a family of free fermions. Just you have to look at them in this way. So you have to introduce non-commutativity. So here is the same. They could prove it only looking through and going through a non-commutative setting. So the idea is that you look at the SPDE. This leaves, so imagine D is 0, okay, just because this lambda is 0-dimensional. So the SPDE, you can write the law somehow of this SPDE using Girsanov theorem, okay, let's say, because you know the law of the Gaussian noise, you pull back. And then you rewrite what you obtain, the density of the solution, as some supersymmetric Euclidean quantum field theory, okay? This is a word physicists use to say you have to introduce also some non-commutative variable which are fermionic to represent this object in a, there is a determinant when you do the change. Essentially, you do a change of variable, there will be a determinant. This determinant you can write in terms of fermions. Maybe somebody of you are familiar with that. And then you have fermions and Gaussian random variable, which have some special symmetry among them, which you don't see. It's a surprise, okay? Even when you do the computation, I don't want to describe this computation here, but the point is that even when you do it, there is a symmetry, which is a rotation between fermions and bosons, which a priori you don't know why it's there. Okay, it was not there. You don't see anything here. But then this symmetry allows you somehow to reduce the dimensionality of your model, because it's symmetric somehow, so you can just remove some variable. And then essentially you prove this, okay? And now, so I like this result very much because you can state it without any fanciness, but I cannot prove it without the fanciness, okay? So I don't know. So if you want this, you can try. I would be very interested to know if it's possible, but I don't know how to do it. I don't even know how to see it without the fanciness, okay? So it's a surprise. There is one case I can do, so let's do together. It's we do some computation. It's the Gaussian case, okay? Because Gaussian looks like a tautology, okay? In the Gaussian case, meaning the potential is quadratic. So your equation is linear, so the solution is Gaussian. The law at a given time is Gaussian. But what is interesting, so there is not much to prove, okay? You more or less confirm the prediction of that theorem. But what is amazing is that actually is the Gaussian with this 4 pi. Okay, so you have to do a real computation And okay, here I did the computation. Okay, the idea is that you can solve this equation very easily because you can invert the linear part. I write in Fourier space. This is a white noise. So this is an explicit representation of this Gaussian random field in terms of white noise. Then you compute the covariance, and you realize that the covariance is exactly what it's predicted by the formula. Okay, so everything is nice. I can prove the theorem in the Gaussian case. If it's non-Gaussian, I cannot do anything unless I go through this very complicated procedure. And we proved recently, so there were a paper in '84 by Klein, Landau, and Perez, which proved essentially this step. Okay, so they started from here, and they proved that you can reduce. And we completed the proof by adding this step, and it's not unconditional, so you need condition to be able to really to do this step, because the equation maybe does not have unique solution, does not have maybe weak solution or multiple, so you don't know. But essentially, with some condition, with Albeverio and Francesco De Vecchi in Bonn, we proved that you can have this connection. Okay, there are, for example, and more recently we have a preprint where, for example, we use it to construct the theory, the stochastic quantization for the Liouville action. Okay, so it's the case where the potential it's an exponential. So this is really like the Gaussian multiplicative chaos you have seen in Jason Miller torque, for example. Okay, and so you can construct. There is Högh-Krohn. Many people introduce this kind of field theory. You can do in the full space, actually. And you can construct this theory up to the critical value of the parameter, which depends on how you parameterize the things, but I think in Jason talk was 2, I think, if I'm correct. Yeah, so the idea, okay, that's just verification. So this is the idea, okay? So we use the elliptic equation to construct a measure which has this weight, okay? And this is what the physicists call Liouville quantum field theory, which has relation also with quantum gravity somehow at some point. Let me go on. Maybe I have 4 minutes, but that's fine. I don't want to tell very much. I want to introduce still another way to look at, to describe, to introduce an equation in a measure. Okay, so here I wrote a bit more precisely, okay, still heuristically, but what should be this 543 theory which you continue to see. Okay, this is one of the simplest examples you can construct in 3 dimensions, which you use to test your theoretical tools. Okay, and formally is the measure on distribution, which is, you see, this part is the Gaussian free field. Okay, it's just the heuristic way to describe the Gaussian free field. And then you have a quartic interaction, which has the good sign, okay? But since the Gaussian free field is a distribution in 3 dimensions, it does not have a very well-defined meaning. So you have to tune the parameter, and you have to take a limit to describe it. And then I want to describe its Laplace transform, okay? So the task is that now I don't want just to construct a measure. I want to describe the Laplace transform. How does it look like the Laplace transform of this measure? So this is a partition function with an external feed, if you think of the physicist language. And then the idea would be that you look at the Gaussian free field, you regularize it at some scale t, and then somehow you couple all the regularizations so that they are a martingale. Okay, that's not very difficult to do. But essentially, you introduce a process, a dynamical picture, where t is the scale of regularization, and wt is it's not a Brownian motion, but it's a Brownian martingale, which has some specific description in terms of space-time white noise, so in terms of a Brownian motion. And then you use it, okay, so this is Gaussian free field regularized, so I look at the I perturb the measure with the quartic potential, and then I still want to look at the Laplace transform, okay? So essentially the goal is to take this limit, to be able to take this limit, okay? This would be a way to construct a measure, okay? You prove that this sequence of regularization has a weak limit as a probability measure. with some tightness. But if you can control this limit, you can do also the tightness part. Okay, you know that the Laplace transform converge. And yeah, so you have this Gaussian martingale, okay? So this is another way to have a time into the problem, to have a stochastic analysis coming in, okay? Because now you have a martingale. You have a filtration, which is not, so this is not physical time either, okay? This is the scale. So you have a filtration which looks at smaller and smaller scale on your problem. So t going to infinity means smaller and smaller scales. This is like a cutoff in Fourier space, okay? So t has to go to infinity, and then you allow more and more frequency in your problem and more oscillations. And then there is a very nice formula which comes from a work of Bouet and Dupuy, which I like a lot, which allows you to express any functional of Brownian motion and the expectation of any function, almost any function of Brownian motion, as a variational problem, a control problem. This is not very unlikely what Antonio was doing in spin glass, I think, using this variational representation to induce some understanding, better understanding. So the idea is that so look again, sorry, so this is the definition of WF. Okay, so you take the log, and essentially you have a formula for the log of the expectation of this functional. So here the Brownian motion is the x, so W is a linear transform because you have to construct a Gaussian free field out of white noise. But this is a function of a Brownian motion, infinite dimensional Brownian motion if you want. And then you have a formula which tells you that this expectation value can be computed as the infimum. You see the log exponential disappeared. Is not an error, okay? It's an infimum over all the expectation of essentially the same functional, but where instead of having the Gaussian free field, you have a Gaussian free field which is perturbed with some unknown function u, which you're allowed to choose. Okay, so you have to take the inf over all the control. It's a control problem, okay? You have a cost function, you have somehow the cost of your control, okay? You cannot use very large control, and what you want is to minimize the value you obtain. Yeah, I think I'm done. And the idea is that using this control problem, you can, again, derive a construction of 543 using you use this control problem, and you use a property of this martingale, and you use estimates, okay? You see this object somehow control the size of u, and you have to prove that this object control all the other objects as t goes to infinity. But let me stop here. I think I'm a bit out of time. And thank you.
Any questions?
So what is the physical interpretation for the phi to the 4-term or the e to the 5-term?
Yeah, there is no physical interpretation. I mean, the point is you want to construct, so somehow Gaussian measures, you remember my axiom, Osterwalder, okay, if you put there a Gaussian measure, what you get is a quantum field theory where particle does not interact, okay? So somehow you will be very happy as soon as you have a theory where you see interaction of particles. And so your measure has to be non-Gaussian, okay? And then it has to be reflection positive, and it has to be Euclidean invariant. So somehow it means that essentially the kind of thing, so let me give you, so I think, yeah. So the kind of thing you can allow as potential has to be integral of local function, okay? Because this is, reflection positivity requires this. And then you need to have, you cannot even have higher power. This would ruin reflection positivity, okay? So the fact that there is only the H1 norm is dictated by reflection positivity. Reflection positivity is similar to some kind of Markov property in the space, okay? Gaussian free field is Markovian if you condition different parts as independent. This is important, so you don't want to ruin these properties. And so you are allowed only local function, and potential phi 4 is okay. And you cannot do higher power, it gets more complicated. And phi 3 is not good because it does not have the good symmetry. Okay. Also because this potential will be unbounded below, so you cannot control it. Okay? So phi 4 is the fast, easy power you can put. Yeah.
Levy, it is related with previous question. You have mentioned convex potential and its gradient. What is the physical meaning in your theory of the gradient of convex potential?
Yeah, so unfortunately, you see, we proved this thing because this is the only thing we could have a convex. So having a convex potential is not easy because you have to renormalize. So I didn't discuss very much this, okay? But the idea is that, you see, that's not very much convex, okay? There is a minus infinity phi square. So you have to, so these objects are formal. Okay.
Semi-convex function? It is not convex.
I think it's very difficult to retain any convexity after renormalization. There is some kind of large-scale convexity, but it's not easy. The function phi you have to put inside are distributions. That's the difficulty. Okay, so you have to renormalize. So this object has to interpret properly, and as soon as you start to interpret, you lose somehow convexity. Because, okay, you see from here, okay, this is a very large negative constant. So every estimate you could try to have from convexity disappear. There is some convexity, but it's not, it may be convex at infinity, some kind of things like this, in large scale, okay?
Thank you very much.
Yeah.
Let's thank Massimiliano again.
Yeah.